Okay, everybody, so we're going to pick up talking about how the atomic orbitals that we talked about in Chapter 6 become molecular orbitals. So we're going to look specifically at covalent bonds for this, okay? So lattice energy is how we look at ionic bonds, so that was the last video. And now we're going to talk about covalent bonding, which is going to look at a new idea, okay? So basically, we already know from drawing Lewis dot structures in Chapter 8 that shared electrons are called covalent bonds. What we haven't talked about yet is how covalent bonds actually sort of form. And so we want to start from our understanding of electron configuration from Chapter 6, right? So pause this video and see if you can remember, using a periodic table, how to write the electron configuration of N2. So you're going to look at each nitrogen separately to do that. So you should come up with a 1s2, 2s2, 2p3 for each nitrogen, where just these outer valence electrons are what you're going to draw in your Lewis dot structure. So for each nitrogen, we have 5 valence electrons. Now if you draw it this way, it's a lot easier to see that we have 3 open sites. I'm going to put X's in each spot to bond. And so if you have another nitrogen, N2, subscript 2 tells us that we do, you could imagine that these empty spaces on each nitrogen can be filled by just connecting them to each other. So for example, I'll use a purple line. We're going to say these two are going to share. These two are going to share, and this is going to get kind of ugly looking, but it's valid as far as Lewis is concerned. They can share there as well. And so that would mean we have a total of 6 electrons being shared between these nitrogens. Oh, I drew my purple line to the X instead of the, hold on. I meant to draw it from the, so each line represents 2 electrons, right? And that's a bond. So we can draw these structures. This is technically a valid Lewis dot structure. It's not very pretty though. I would rather show the bonding electrons between the 2 atoms, which is where they are physically in space, and the non-bonding electrons on the outside. So this is the Lewis structure we would get for nitrogen. So in order to understand how these 6 electrons get organized in a molecule, we want to connect with our image of what an s orbital looks like, which should just be a sphere, right? Circle if you're drawing in 2 dimensions, but a sphere really. And then a p orbital are the ones that look like balloons stuck to each other. So that would be 1 p orbital. And we have 3 of those that are occupied by electrons when we're talking about just the atom. Okay, so I like these little simulations to show us what happens when we start talking about molecular orbitals. So first I decided to click on the hydrogen one, which is a little more straightforward because it's just 1 electron from each hydrogen in the 1s orbital level. All right, and so what we're going to do is you can see these tiny darker red circles. These are the nuclei, and this drawing is showing us what the molecular orbital shared by these 2 hydrogen atoms looks like. It's kind of like an oval, essentially. So we went from having, wait for this GIF to loop. We went from having 2 spheres to having sort of this melted together oval, right? So that's what hybridization is. And you can see that this is called a sigma bond. Whenever we have a single bond, we have 1 sigma bond. Sigma, as we're going to learn, has something to do with the shape of this molecular orbital. Okay? It's directly located between these 2 nuclei. That's what a sigma bond does. Nitrogen's a little bit more complicated. So you can see the nucleus, and then you can see the 1s, and then the 2s, and then we have some 2p molecular orbital, and all of these are, these outer, the 2s and 2p, are involved in making this oval shape this time. So you can see we start out with 2 independent atoms, and then their valence electrons, the 2s and 2p, kind of just mush together. This is an animation based on some really complicated math, okay? And so the computer is doing some what we call wave mechanics calculations here. And so the particular kind of math is just called hybridization. We don't need to replicate that math, but we do need to understand how they do it, okay? And so when we have just hydrogen, we start out with two 1s orbitals, just like we saw in the animated version of this. And each hydrogen is going to share one of their electrons to make a bond. And that's where you get this kind of peanut-shaped or oval-shaped molecular orbital. All right, we draw that on the Lewis dot structure by showing the two hydrogens shared in the middle. And you might draw that as a line, or you might draw it as dots like they do in this picture, right? So I prefer to do it this way, but it's both correct. When we do the line or the dots in the middle, we're saying those electrons belong to both of these atoms. They don't belong to only one or the other, which is different from an ionic bond. A reminder that we can use electronegativity to determine whether we should be drawing our Lewis structures as an ionic bond or a covalent bond. And we can use it to determine whether a molecule is going to have a dipole. So when you have bonds that are very different and an asymmetric molecule, then that means the molecule has a positive area and a negative area, which is going to be called a dipole. Hydrogen doesn't, because the electronegativity difference between these two is 0, but other molecules will. Okay, so in the case of nitrogen, let's imagine one s orbital and only one of the p orbitals, the one that goes side to side, can bond to each other. So when things hybridize, when we do that math, you actually get some positive interactions and some negative interactions, because these are waves, right? So we're showing them as like a static cartoon picture. But remember, all the things we learned in chapter 6 still apply. These are waves. And sometimes when waves overlap, they do it constructively. So for example, if I take this sine wave, this is my 0 point, and I take, let's do a green one just to be different. And I take this sine wave. If I add these two together, they're equal and opposite in every position. So adding the green wave and the blue wave together would get me nothing. That's called destructive interference, right? That means they cancel each other out. So if this was a sound wave and I had two overlapping sound waves with the exact same characteristics but shifted half a cycle over, just like this picture shows, we would end up hearing nothing if we were standing in that spot. This is relevant for those of us who have ever tried to make surround sound in a home. The shape of the room will dictate where the destructive interference happens, but there is likely to be places in the room where you can't hear as well as other areas, and that's because the waves are overlapping in such a way that they cancel each other out. That is an example right here. That's what's happening in these smaller areas. These are destructive interference. You don't get as much electron density on those sides. The other places where the lobe of the p orbital is bigger, right? So here and here, these are constructive interferences. So constructive mean the waves add up, right? So if I have, well, that's an interesting sine wave. We'll go with it. If I have something that looks like this, and I'm adding one that is only just slightly out of phase from this one, so it might be something like this. When you add each of these points together, here and here, here and here, here and here, when you add each of these points together, you're going to get areas where they add together to make a bigger wave. So here, for example, we would add this much to the top of the curve, so your point ends up here. So you end up with an even bigger curve in some places than you started with. That's what's happening when we do hybridization. Okay, so the bigger areas are constructive interference of waves, and the smaller areas are destructive interference. And so when we add these two things together, we get two different shapes, and we will collect them together and call them sp hybrid orbitals. All right, and so this is what the shape looks like total when you take the top and the bottom and add them together. And you can see the little destructive parts are buried inside of the bigger picture here. We still have nodes, okay? We still have areas where electrons cannot go, just like we did before, right? No electrons are on the top or the bottom, for example, or the front and the back of this molecule. So, sp hybridization means we have two orbitals involved, one s and one p. And it means we can only have orbital overlap in between the two atoms. All right, so when we look at this example of BeF2, BeF2 is sp hybridized. That means the Be has orbitals that look like the one up here, sps. And it comes from forming a 1s orbital and a single s orbital and a single p orbital get sort of averaged together to give you these purple regions. That's a molecular orbital. The fluorines have to use one of their p orbitals to bond with the sp hybrid orbital on the beryllium, on the Be here. That means that these electrons can only exist in between the Be and the F. So we call this a sigma bond. So when the electrons are between the atoms, directly in between them in space. Okay, so sigma is kind of like a physical location and shape. Okay. And so you see we have two sigma bonds in this molecule. We have one on the left and one on the right. But in both cases, those pairs of electrons are located directly between the atoms that are bonded. For a little bit more complicated arrangement, we will look at sp3 hybridization because it is one of the most common that you can have. It comes from a single s orbital and all three of the p orbitals. Adding all together, hybridizing, right? It's not really adding, but hybridizing, and we get some constructive areas and some destructive areas. And so you get four different shapes from doing that because we started with four orbitals. And we will take them all together and collect them. And of course we get this shape where each purple balloon is a hybrid orbital. We get four domains doing this, right? That's because we used one s and three p. So 1 plus 3, we get 4 domains. So of course, if you remember from the VSEPR section, oh my goodness, hold on. If you remember from the VSEPR section, this is sp3 hybridized, which means the shape, the electronic geometry, 4 domains, right, we said is tetrahedral. Now, if there's an atom in every location, each bonding site has an atom, then we would also say that the molecular geometry is tetrahedral, but we don't know that from just this picture. This is just showing us the electrons. All right, and so our basic process here, again, this is review from lab, so hopefully you're familiar with it. You start by drawing the Lewis dot structure. You use the VSEPR table to figure out the electronic geometry and the molecular geometry. Hybridization is based on electronic geometry. So for example, if I found that I have an electron geometry that's linear, that means I would have 2 total domains, then it's sp, 2 domains, 1s and 1p. So the domains are equal to the number of orbitals that are used to hybridize. If I have an electronic configuration that's trigonal planar, I'll have sp2 because 1s and 2 p's are needed to make 3 molecular orbitals. All right, and so you keep going that way. 1s and 3 p's is sp3. And so you just keep going. All right, so we already talked about how a sigma bond exists between 2 atoms, right? And so here we have, in this case, two p orbitals that are overlapping end on. And you can see this is a fairly substantial amount of overlap, right? They're sharing quite a lot of their orbitals. The electrons can be anywhere in the pink area, but they're very likely to be in the shaded black area because that's where both orbitals overlap, right? But this depends on bond polarity. Maybe they like to spend more time on the left than the right, whatever. But all in all, the shape is the same, and these electrons are confined to being in between the two nuclei. We call that a sigma bond. When we have double or triple bonds, so it's worth noting, all single bonds are just a sigma. But when we start having double or triple bonds, you get to have the sigma in the middle still, but in addition, we have to fit another bond for a double bond, okay? So a double bond will also have one pi orbital, one pi molecular orbital. They come from when you have the p orbitals on the top and the bottom. Oh, the last one got a little funky, but you can imagine it. When you have the p orbitals that go on the top and the bottom, and they hybridize, that's where you get this kind of weird shape. The first pi orbital, so when you make a double bond, it belongs on the top and the bottom surface of the atoms. The sigma bond would still be in here in between. We're not drawing it on this structure because it can get a little difficult to see, but it's there. So a double bond is one sigma and one pi. Okay. The pi bonds are weaker than the sigma bonds because there's a lot less of each orbital involved. So when you overlap two things end on like this, it's a very strong interaction. It's a very strong bond. Pi bonds are just kind of smeared sideways, right? So they're like much less closely associated with each other. Okay. That doesn't mean the distance between the nuclei is shorter, though. As it turns out, when you make a pi bond, you have to scrunch the two nuclei a little closer together to get these to overlap. So a double bond has a shorter bond distance, and total, if you add together the sigma bond and the pi bond, it is also a stronger bond. But if we have to break one, the pi bond is the weakest of the two that you have in a double bond. Okay, so here's our Lewis dot structures, right? And so when you have hydrogen, H2, there's only one sigma bond. The electrons spend all their time in between these two nuclei. In this drawing, this is ethene, we have a double bond here in the middle. That means there's one sigma bond where the electrons are between the two carbon, and there's also a pi bond that goes on the top and the bottom. When you have a triple bond, like nitrogen, going back to this example, you're still going to have the sigma bond that goes between the two nuclei. You're also still going to have the electrons that go on the top and the bottom of the nuclei. But then you have a cloud that's shaped the same as the pi bond on top and bottom, except it's going towards us and back into the board. So you end up with two pi bonds, one on top and bottom, one on front and back, and one sigma, which is in between the two nuclei.